Okay, so let's start today's class. So in the previous class, we learned how to organize data paths and then why the control unit is required for this single cycle processor design. So in the first class of the chapter 4, we learned which step is required for executing instruction. So actually, I categorized the required steps for 5 steps as 5 steps, like instruction fetch and instruction decoding, execution, memory, and write back. So we learned why these steps are required for executing RISC-V instructions. And then in order to execute a certain instruction, then actually for each step, so we learned which data path element. So data path element means that it is the hardware component that is used for processing data or generating addresses in the computer processor. So that is the definition of a data path element or data path. So we learned which data path is required for each step of this computer processor, single cycle processor. So we learned that for the instruction fetch, we need program counter register and instruction memory, okay? And then also we need this adder because we always, when after one instruction is executed, then the next instruction should be executed in the computer processor, right? So that means the PC is just increased by 4, right? Because the size of the RISC-V instruction is 32-bit, okay? So we need this adder. So PC plus 4 is generated, okay? And then the instruction comes out from this instruction memory, and then in the instruction decoding stage, not stage, it's an instruction decoding step. This instruction is connected to what data path? So register file. Okay, so sometimes I use the RF. It's the abbreviation of the register file, and then this instruction is connected to the immediate generator. So when we learned about the instruction decoding step, we classify the RISC-V instructions as the R-type instruction and immediate type, the like load or store instruction. Also memory instruction, actually the memory instruction is the immediate type instruction, and the branch instruction, so conditional branch. So, and then we also learned that instruction of the RISC-V, each field is assigned for the destination register number or source register numbers or immediate field. So this instruction that comes out from the instruction memory directly connected to register file and instruction generator, okay? And then the two source register numbers like RS1, RS2 is given to the register file, and this register file make the output of this register data. Okay, it's a 64-bit data. So this data is delivered to the ALU because we need the arithmetic and logic operation. So then this operation is performed by ALU. So sometimes the second input of the ALU can be immediate value. So we need the MUX here, and then also we need the selection signal here, and then through this mux, we can select the one input from register file and then another input from immediate generator. Okay. For the memory instructions like load, double word, or store double word, then the ALU is used for generating addresses. Okay, because the address is calculated like a RS1 plus immediate value. Okay, so this generated address is given to the data memory. So in order to access the memory, then we need the address and then some control signals. And then the data can be out from this data memory for the load instruction. And then data is written to the data memory for the store instruction. Okay. Also, the write back. So write back means that the data generated by RISC-V instruction is written back to the register file. That is the write back. Okay. So this written back data can be the data from data memory or the data from ALU. Okay. So we need to select this result with the, and then based on the instructions. So for the load instruction, we need to select the data from data memory, and then for the R time instructions, then we need to select the data from ALU. So that's why we need this mux. Okay, and then for the branch instruction, we need the adder here, and then also we need the mux because based on the result of the branch, then we can select the next instruction like a PC+4 or the target of the branch. So if the selection is required, then we need a multiplexer. Okay. Okay. So I hope everyone can understand how to organize the data path or how to connect the input and output ports of data path element to organize the single cycle processor. Okay, so you need to understand because so if you cannot understand that this part, then you cannot move on to the next topic. It's a pipelining design. So please study hard and then try to understand how to organize these data path elements and then how the data, that means the instructions or some data from register file or data from data memory or ALU is connected to each data path element. Okay. And then I mentioned that. So we just define the data path element for the single cycle processor, and then we connect the input and output ports of the data path element. So what is missing? Control signals. Because data path element is controlled by control signals like this leg write, and then ALU operation, and the mem write and mem read. Also, this single cycle processor includes several muxes, multiplexers, and then multiplexer requires selection signal. So that is also control signal. Okay, so these are also control signals. So these control signals should be also generated. Okay. So I said, so we need a control unit, and then this control unit works based on the instructions. Okay, so we will learn about some control signals in this class. So in the late part of the previous class, we just covered the ALU control. Okay, so this is ALU need to receive these control signals like ALU operation, because the behavior of ALU varies by instructions. So this is the required operations for ALU. So for example, for the load or store instruction, that is the memory instruction. So the function of the ALU should be add, because right, we need to perform RS1 plus immediate. And then for the branch instruction, and then in this course, we just this processor just to support the BQ instruction. So we could just compare the two values of registers. So in order to compare the values, we need to perform the A minus B. So for the branch instruction, the ALU needs to perform subtract operation. Then for the other R-type instruction, so this processor just to support the AND, or add, and sub instructions. Okay, so for the R-type instructions, the required operations for ALU is determined by the kinds of R-type instructions. So if the end instruction is executed, then the ALU need to perform bitwise AND, then or the bitwise or. For the add instruction, so ALU need to perform add, and then for the sub instructions, then ALU need to perform subtract. So if we see the all required operations by ALU, then we can know that ALU needs just 4 different operations, AND, or, add, and subtract. And then these 4 different operations are selected by ALU control signals. So, and then I explain why actually there are 4 different operations. So we need only 2 bits for this ALU control signals, but I explained that the normal RISC-V processor support the more operations, like more instructions. So like some shift instructions or exclusive OR instructions. So in order to support the more operations or more instructions, ALU needs to support the more operations. So that's why the ALU control signals have 4-bit width, but actually we need only 2-bit. But in this course, we assume that the ALU control signal is 4 bits. Okay. And then, so in this slide, the operation of the ALU is determined by the instruction types, like memory instruction, or branch instructions, or R-type instructions. And then the detailed operation of the R-type of ALU is determined by the kind of R-type instructions. So I already explained. So in the previous class, I explained that we first decide the ALU OP control signal. So this ALU OP control signal is determined by instruction types. Okay. So for this load and store instruction, this is the memory instructions. So we can the memory instruction is issued to this processor. Then ALU need to perform add operation, and then how can we know, oh, this instruction is the load instruction, or this instruction is the store instruction? By checking the OP code field in an instruction, then we can know the type of instructions. Okay, so I also explained. So this is the IV32I instructions. And then if we just to see the OP code field, so we can easily know that, oh, if the OP code field is 000011, then that is the load instruction. So okay. And then store instruction, so here. And then the R-type instruction, this is the R-type format. So we can know that for the R-type instruction, the OP code is 0110011. Okay. So if we just check the OP code field of the instruction, then we can decide the instruction type. And then based on this instruction type, ALU operation mode is determined. So that is the ALU OP control signal. So that means ALU OP control signal. Okay. So in this example, if for the memory instruction, the ALU OP becomes 00 here. And then if for the branch instruction, the OP code field is 11000011. So the ALU OP code becomes 01, okay. And then for the R-type instruction, I already explained. Then ALU OP becomes the 10. So if the ALU OP is 00, we can just perform add operation. And then for this add operation, the ALU control signal becomes here 0010. Okay, this is the add operation of ALU. So here, and then if the instruction is a branch instruction, then we need to perform subtract, and then ALU controls bits should be 1001. And then for the R-type instruction, if the ALU OP is 10, then this required operation of the ALU is determined by kind of R-type instructions. So these are R-type instructions like SLL, SRL, SRL. These are shift instructions. The arithmetic instructions, add and sub. And the logical instruction, exclusive or and AND. And then also we can use the compare instructions, okay, here. So then based on the detailed instructions, then we can select the ALU control bit, like a 0010, 0110, like this, okay? Understand? So we can know that ALU control signals include ALU OP here, ALU OP here, and then ALU control signal. Okay, so ALU control signals are determined by instructions from instruction memory. Okay, because you can get instructions from instruction memory, okay, by PC address. So this slide also explained what I explained. So I will skip here. And then if you see that this so well organized IV32I instruction table, then you can easily know which operation is required. So how to generate some required control signals for ALU. Okay. Okay. So this is the completed single cycle processor design, which includes control unit. So control unit is here. So as you can see, this control unit receives instructions, okay, here. But we can find that only the pin number 620 is given to this control unit. So what is this part? This part is the OP code field on instruction. Okay, so which part? This part. So, and then as you can see, this OP code is here, and then actually based on this OP code, then we can easily know the types of instruction. Okay. So if we see the OP code field of this list of 5 instructions, then we can easily know, oh, this is the load instruction. It's a kind of load instruction. It's a load instruction and store instruction. Then, oh, this if OP code is, then it's R type instruction. And then actually the I type instruction is not supported by this processor. But if the OP code field is 001, 0011, that means that this is the I type instructions. Okay. And then also, if the OP code is 110011, so that means this is the SB type instructions. Okay, that is the conditional branch instruction. And then for the jump instruction, the OP code field has 110111. So what can you find? So based on the OP code field, we can know the types of instruction. That's why this control unit just receives the only 7 bit from instructions. Okay. And then, so based on this OP code, then we can decide the ALU OP signal. So 00 means it's a memory. So ALU OP. 00 means the load or store instruction. And then 01 is the branch instruction. And then 10 means the R type instruction. Maybe 11 can be I type, maybe. But so as I mentioned, this processor just support the only a few instructions. So I type instruction is not supported by this design. Okay. So under here. And then also we can find the additional control signals like branch, mem read, mem to rev, mem write, ALU source, and reg write. Okay, and then we can know that these control signals are also determined by OP code in an instruction. Okay, and then this ALU OP is given to the ALU control unit. Okay. And then this ALU control unit finally generate the ALU control signal. So 4-bit control signal here. Okay. And then this ALU control signal just received the instruction bit number 30 and then 14 to 12 from an instruction. So which part? So actually this part is the function 3 and then function 7. Understand? So for the R type instruction is detected, then we can check the function 3 field like here, 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 here. Okay. So based on this function 3 field, then we can know the detailed instruction. So like here, then we can know also which operation is required for ALU. So but we also need the function 7 field, right? Because if you see the add instruction here and then solve instruction is here, then we can find that so add and solve has the same OP code field, and also the function 3 field is the same. Then how can we distinguish the add and solve? So we need to check the function 7 field here. So which bit is different? So this bit is different, right? So that's why this ALU control requires the instruction bit number 30. Okay, right? Because the function 7 field is here. Okay, so that's why. So in order to distinguish A and sub, then we need this bit inst 30. Okay, and then so this processor supports the or instruction and instruction. So as you can see, the function 3 field of the or instruction is 110, and the AND is the 111. So we don't need to check the this instruction pin number 30 of the instruction, because we can just distinguish or and instruction using function 3 field. Okay, so by checking this opcode field and the function 3 field and the function 7 field, we can determine the required operations for ALU. Okay, that's why this ALU control received the pin number 30 and then 14 to 12. Okay, and then the final ALU control signals are generated from ALU control unit. That's it. So we learned that how to generate the ALU control signals. So these ALU control signals are generated based on the instructions. Okay, then let's see how the other control signals are determined by an instruction. So let's see the R-type instruction. So R-type instruction. So what is the example of the R-type instruction? So you will be very familiar. So add X1, X2, X3. So this is the destination register. This is the RS1. This is RS2. So what is the required operation of this R-type instruction? So read two register data from register file and performs the defined operation using ALU, and then store this ALU result to register file using this destination register number. That is the operation of R-type instruction. Then how can we generate the control signals? So this is the control unit. Then let's see how the control signals are determined. Okay, how about the branch? What is the value of this branch instruction? The branch control signal if the R-type instruction is executed in this processor. So we are executing R-type instruction. So what is the value of this branch? 0, right? This is 0 because this is not a conditional branch instruction. And if this is 0, then you can find that this is the AND gate, then the output of this AND gate is always 0. And if 0, then what is the next instruction? So the next instruction is the PC plus 4. So that's just next instruction, not target of the branch. Okay. So this branch control signal should be 0. Okay. How about the mem read? Mem read should be also 0 because this is not a load instruction. So we don't need to access this data memory. So one student asks about this mem read signals. This is very good question. So if you are you have a question about the data memory control or the register file control, please find some question on the Piazza. So that was the very good question. Okay, but this memory signal, memory control signal should be 0 because this is not a load instruction. How about mem to read? Mem to read should be also 0. So this control signal is connected to the selection port of the MUX, and then output of this MUX is the result from ALU if the selection signal is 0. And this R-type instruction requires to store the result from ALU using the destination register number. Okay, so this path should be activated. That means that selected. So mem to reg should be 0, and then ALUP. So we already learned this should be 1, 0 for the R-type instruction. How about the mem write? It's also 0. It's not SD. It's not store instruction. And how about the ALU source? What is this value? So this value is, so you can find that, oh, this control signal is connected to the selection port of this MUX. Then you can find that if this signal is 0, the selection signal is 0, then the data from the read data, data from register file is delivered to the input of ALU. We already learned that, oh, this is the R-type instruction. R-type instruction requires the 2 operands from register file. So like read data 1 and read data 2. So this read data 2 should be connected to the ALU. And then for this connection, the ALU source control signal should be 0. Because when it's 0, then this is connected. How about the leg write? What is the value of a leg write? It's right, it's 1. So what does leg write mean? So write operation is performed in the register file if the leg write is 1. And then what is the definition of R-type instruction? In the R-type instruction, the result from ALU is written back, it's stored, written back to the register file. That means that, oh, this write data and is stored in the register file using the destination register pointed by this destination register number. Okay, and then for this operation, we need to set the leg write is 1. So also, I explained why write enable signal is required in register file and memory. Okay, so you can find the answer in the piazza. Okay, so we created all control signals for R-type instructions. Okay, so that's not difficult, right? So these control signals are generated by instructions. Okay, then actually in the RISC-V, this control signal just received the 7-bit OP code field. So based on this OP code field, we can easily generate these control signals. Okay, how about the load? OP code is load instruction 00001. Okay. So what is the behavior? What is the operation of a load instruction? Load x1, x2, immediate. Well, you can like this immediate x2. So that is the load instruction. So for the load instruction, this load instruction reads that base address from register file and then performs the add operation with the immediate value, and the data from data memory is stored in that is written back to the register file. Okay, that is the operation by load instruction. Okay, so continuing, how about the branch? It should be 0. This is not a branch instruction. It's very simple. So this output of AND gate is always 0. Okay, regardless this signal. Okay, so the next program count should be PC plus 4. Okay, and how about the mem read? This should be 1 because this is load. So we need the memory read operation, data memory read operation. So this mem needs to be 1 because it's not 1 because this is load instruction. How about the mem to reg? It's 1, right? Because I said that the data from data memory is written back to the register. So we need to select this path, okay? Then in order to select this path, then the selection signal should be 1. So mem to lag should be 1. ALOP was 0, 0. We learned. How about the mem right? It's 0. This is not a store instruction. And then how about the ALU source? It's 1, right? Because for this second input of the ALU, this should be immediate value. Okay, this path should be selected because this means the immediate value for the load instruction. How about the leg right? It is 1 because the data is stored in the destination register. Simple. How about the BQ? Branch is 1 because it's branch instruction. Okay, so because this signal is 1, the output of this AND gate, AND, is determined by this input 0. Okay, because the one input of the AND gate is 1. Okay, so if the condition of the branch is true means that it's 0 equal, so it's true. Okay, 0 equal 1. So then if this is 1 and we set that this branch control signal is 1, so output of this AND gate becomes 1. So this path is selected. Okay, so this is the target of a branch. Okay, if this 0 is 1. Okay, how about the mem read? It's 0 because it's not a load instruction. About mem to reg, actually don't care because for the branch instruction, the data is not stored in the register file. Okay, so actually the leg right is, so the leg right is 0. So if we see that this branch instruction like x1, x2, and target, there is no destination register. So that means that the data is not returned back to the register file. So actually any data can be delivered to the register file because this write operation is not performed. So actually the mem to read is don't care. So don't care means that it can be 0 or 1, but it does not change the operation of the BQ. Okay, so don't care. How about the ALOP? It was 0, 1. We already learned. How about the mem write? It's 0 because it's not a store instruction. How about the ALU source? Right, it's 0. It is 0 because branch instruction requires two operands from registers. Okay, so this path and this path should be activated. So ALU need to receive the x1, x2, that's the data from the register file. They need to compare these two data from register file. So that's why ALU source should be 0. So all control signals for branch instructions are determined. It is determined by OP code. What is the OP code? OP code is 110011. So PQ instruction OP code field is the 110011. So that means 110011 is given to this control unit, then this control unit generates these control signals. Okay. Oh, we missed the store instruction. The store instruction is maybe we can for the store instruction. Oh, where is the store instruction? Oh, I missed the store instruction. Okay. How about the store instruction like SD? So let's think about the store instruction. Okay. So what is the behavior of operation of a store instruction? That is the SD, X1, immediate X2. So for the store instruction, the base address is read from the register file, and then this base address is added to the immediate value. And then how about this X1? This X1 is the it's the source register. Source register. So store instructions require two data from register file. Okay, two operands, two data. Okay, then how for the store instruction? So just ignore this load. So for the store instruction, the OP code field is 10111 010011, right? 010011. This is the OP code, right? Right. So if the OP code is 01000011, then that means that it's the store instruction. How about the branch? Branch should be 0. It's not branch. How about the mem to read? It's 0 because it's not a load instruction. How about the mem to read? Actually don't care. It's like a branch instruction, right? For the store instruction, the data is not returned back to the register file. So the leg write of the store instruction is 0. So actually any data can be delivered to this write data. It's the same to the branch instruction. Okay. So mem to leg should be mem to leg is don't care. It's don't care. How about the ALUOP? ALUOP is the 00 we learned. How about the mem write? It's 1 because it's store instruction. Okay. It should be 1. How about the ALU source? Right, ALU source should be 1 because we need the immediate data for the ALU operation. Okay, so this path is activated for the ALU operation, for the ALU operand, the second ALU operand. Okay, and that's it. Okay, so for this store instruction, we can find that this the second data out from the register file, the read data 2 is connected to the write data. So because this mem write is 1, the write operation for this data memory is activated. So this write data is returned to the data memory. And then we can find that, oh, this data is directly connected from read data 2. Okay, this is the store instruction. And that's it. So this is the single cycle processor design. So that means that for every clock, the data, the instruction is read from the instruction memory by program counter. So actually the program counter is synchronized by clock signal. Okay. So that means that for the every clock, the PC value is changed. And then if the PC value is changed, then address for this instruction memory is changed. That means that for every clock, it can be the different instructions from instruction memory. Okay. So, this single cycle processor, if an instruction is read from the instruction memory, then this instruction complete its operation before the next rising edge of the clock. Okay, that is the single cycle processor. And then it's the completed single cycle processor design. So we first define the data path, required data path, and then we organize the data path. That means that we just connect the input and output ports of each data path element. Then we also include some basic data path elements such as multiplexers. And then we create the control unit and then connect the control signals from this control unit. And then we learned how to generate control signals based on instruction here. Okay. So I think is it difficult or I think it's not difficult. So because we can easily generate the control signals from this control unit. Okay. Mhm. Okay. So I will conclude the single cycle processor design. Actually, this is the very simple design, and then but performance is not good. Why? So in the first class of this chapter 4, we learned about the digital system design basics. So actually, the basic digital system is composed of combinational logic, and then input of the combinational logic is connected to the D flip-flop. Oops. And then the output of this combination logic is also connected to the D flip-flop. And then we learned that the delay, delta T is a delay. Delay of this combination logic should be less than the clock period. Clock period. That means the time between the rising edge of the clock and then the next rising edge of the clock. That is the clock period. So that means the maximum delay of the combinational logic determines clock period, because delta T should be less than clock period. If the delay is long, the delay is very long, then we need to use the slower clock. So what's the problem? So this is the single cycle processor design. So what is the longest delay? So actually these data path elements, and then these data path elements are basically combinational logic. So that means this data path element has delays. So that means the input signal is given to this data path element, then output signals are generated after some delays. Okay. So input memory has the delay, register file has delays, and then also ALU has delay, the data memory has delay. And then the final data is written back to the register file. That also takes time. So in order to complete the required operation of an instruction, then it takes time. And then usually these delays are the sum of the maximum delay of these data path elements. Okay. So let's think about the load instruction, not store. Sorry about that. So let's see how the load instruction is executed in this single cycle processor. First, the PC is changed. So the PC is determined, and then this PC is delivered to the instruction memory. And then this PC is given to the instruction memory after some delay, like let's see, it's T1. And then the instruction is out from the instruction memory after delta T1. And then we need to access the register file. So let us assume that this delay of the register file is delta 2. And then this instruction is delivered to the read register number 1. Okay. The source register number is delivered to this port. And then after delta T2, then data comes out from the registers, right? And then this data is delivered to the ALU. So actually the immediate generator and the MUX has also delays, but we just ignore this part. And then ALU has also delays, like delta T3. And then after this delay, the address is generated. And then we access the data memory. It also has the delay delta T4. The MUX has also delay, but just ignore the MUX delay of the MUX. And then the data from data memory is written back to the register. And then for this write operation, we need also time. It takes time. That is the delta T5. So for the load instruction, these all delays are delta T4 plus delta T5. So these all delays are included in the delay of load instruction. And then this is the longest delay in the single cycle processor operation. So this longest delay determines TC, clock period. Okay, what's the problem? Execution time is instruction count, CPI multiplied by TC. For the single cycle processor, CPI is always 1 because it takes 1 cycle for executing 1 instruction, right? And then this IC instruction count is determined by software, like the user program, user application, and compilers. So the hardware cannot change instruction count. Then it doesn't matter. TC determines execution time. If the TC is for clock period is very long, then ET will be also very long. The execution time will be very long, then it will, that means that the performance is bad. Then we learned that the TC is determined by, TC should be bigger than the accumulation of the all delays of the data path element. So this long clock period degrades the performance. Okay. That is the performance issue of single cycle processor design. Okay. Because in the single cycle processor design, the clock period should be bigger than the summation of all delays of data path element. That means the TC is very high, so the performance is very low. Okay, so how can we increase the performance? So in order to increase the performance, actually we need to reduce the TC. Okay, then how can we reduce the TC? That is the pipelining. Okay. Okay, so so let's learn what is the pipelining. So, okay. So actually this is the end of the single cycle processor design, and then the midterm will cover until this part. Then let's move on to pipelining. So what is the pipelining? So if you see that this figure, then you can find that this figure just shows the required steps for laundry. Okay. So for this laundry, then let us assume that for a single laundry task, then we need to use the washing machine and then washing machine and then dryer, and then we need to also fold the clothing, and then we need to pack the clothing to the closet. Okay, Let us assume that this laundry task, a single laundry task, is composed of these 4 steps. So if we just start the single laundry task here, and then let us assume that each step takes 30 minutes, and then for the last task, the last step, it takes 2 hours. Okay, so if there are 4 tasks, then we need 8 hours for complete these 4 laundry tasks. But what's the problem? So how about the washing machine? The washing machine is used for 30 minutes for this first task, and then this washing machine is not used. And then it's idle because other components are used. How about the second task? This washing machine is just used for 30 minutes for the second laundry task, and then idle. It's not used. It's the same to the other tasks. What's the problem? The resources. It's a resource. It's a hardware resource. The hardware resources for a certain task is wasted because it's not used. So let's think about the load instruction of the single cycle processor. So we just use the delta T1, delta T2, delta T3 is a delay for delta T5. So for the delta T1, we just use the instruction memory. And then for the delta T2, we use the RF register 5. This ALU is used. This is the data memory. And then it's also RF, but it's write, it's read. So what's the problem? Even though these hardwares are used for, these data path elements are used for executing load instruction or certain instruction, but this data path element is used for only a short time, and then this instruction memory is not used for this period, very long time. That means this hardware resource is wasted because it's not used anymore for this instruction. That is the problem of single cycle processor design. But if we can just divide the required steps to the multiple parts, and then if we use the pipelining process to this laundry task, then we can reduce the execution time. We cannot reduce the execution time of a single task because if this task starts from 6 p.m., this task completes at 8 p.m. So actually the completion time is the same for the single task. But what is the benefit? The next task can start earlier. Okay, and then how can we start the next task? Because the washing machine is idle after 30 minutes. So the next task can use this washing machine. Okay. Then the next task can use the washing machine. So what is the benefit of this pipelining? These resources are not wasted. Okay. If this task is serialized like this one, we know that this hardware resource is wasted because there are long idle time within a clock period. But if we use the pipelining manners, then this hardware resource is used during each time slot, So this hardware resource is not wasted. So benefit is that the next task can start earlier. And then if there are many tasks, then we can reduce the total execution time. Okay. So just to stop. So in this analogy, we just compare the performance of the single cycle. so non-pipelining laundry task and then pipelined laundry task. What is the speed up? For this serialized laundry tasks, then the total execution time is 8 hours. It's 8. But for the pipelined laundry tasks, the total execution time is 3.5. So speed up is the 2.3. So performance is improved by 2.3 times. That is the benefit of pipelining. So what does that mean? So when I mentioned the execution time of the single cycle processor, so execution time is that instruction count multiplied by CPI multiplied by TC. So what is TC? TC for this serialized laundry task. That is the 2 hours. Okay, but how about this one? This is the 0.5 hours. And then we also, without this pipelining, you can know that the instruction is executed every cycle. So CPI is nearly 1. Instruction count is not influenced by hardware, but what is the benefit of pipelining? We can reduce the clock period. So in this example, we can reduce the clock period to the 1/4 of the original clock. That is the clock period of a single cycle processor. It becomes the number 4. So that means the execution time, the performance is improved 4 times with this pipelined processor. Okay. So that is the benefit of pipelining. The first, we can reduce the waste of hardware resources. The second, we can increase the performance of processors. So actually this pipelining mechanism is widely used for our real life because, so think about the conveyor belt in the factory, the car factory. So in the conveyor belt, some task is done by this worker 1, and then after this task is done, then this object moved to the worker 2, and then the next task is done by this worker 2. While this worker 2 is doing his or her own task, then this worker 1 is doing new task. That is the conveyor belt in a factory. And then it's the same to the pipelining. So the definition of pipelining means that the task is divided into multiple parts, and then these multiple parts are assigned to a certain hardware. That means the data path element. And then if the data path element complete each operation, then this instruction, like or some object is given to the next part, and then this hardware element, the data path element, receives the new task. That is the pipelining. So why do I split the required tasks to 5 steps? Because we will learn about the 5-stage pipeline. Okay, so this is the required 5 steps for executing instruction. So it's the instruction fetch, instruction decoding, execution, memory, and write back. So we can easily split the required steps for executing instructions. And then we already defined which data path is required for these split tasks, like instruction fetch, decode. So for example, for this instruction fetch, we need the PC and instruction memory. For ID, we need the register file for read. And then execution, we need the ALU. For the memory is the DMEM, data memory is required. Output write back, we need to register file and the write. So, like this pipelining, we can just split the required task for executing an instruction. Then we can organize the computer processor with a pipelining manner like this. Okay, it's a very great idea. Okay, that is the benefit of pipelining. So this pipelining is very important topic in this course. So I hope you can, I hope you surely understand this pipelining architecture. Okay, so okay. So I'll stop here. And do you have any questions? Okay. Thank you for listening. And then good luck for the midterm exam. Bye, guys.